Good morning to all, my dear students. This is our channel, Physics Gallery, Asha. And today we entered into the new chapter of our plus 2, a very good chapter, an interesting chapter called as Moving Charges and its Magnetism. We are discussing moving charges and magnetism. Our fourth chapter. We reached to our fourth chapter, moving charges and magnetism. Okay. That is, in this chapter, we have to discuss about the magnetism of moving charges. The magnetism of moving charges. That is, moving charges means current. A current carrying conductor shows certain magnetic property, magnetic effect. And the magnetic effect of a current carrying conductor was first identified by a teacher like us, by a professor, by a scientist, Hans Christian Ørsted, also pronounced as Ørsted, as you like. Hans Christian Ørsted was the scientist who first identified the magnetic property of a current carrying conductor. Okay, that is, he accidentally placed a compass needle near a circuit. Okay. And when he switched on the circuit, he can see certain deflection is caused in the compass needle. When the circuit was closed, he saw some deflection is shown by this compass. Okay. That is, a compass can undergo deflection only in the presence of a magnet or the magnetic property provided by the magnet. But here there is no any magnet, only a circuit having the resistance R, a battery which can provide a potential of V. When the circuit was closed, the compass needle deflects. That means this deflection is caused by the current in the circuit. Okay, when he switched off the circuit, what happens? The deflection in the compass needle stops. Similarly, when he reversed the direction of current, now the current was this. When he reversed the direction of current by reversing the battery, now the current is in this direction. Okay, the deflection, in earlier case, if the deflection is towards the right, now the deflection is towards the left. That is, when the direction of current is reversed, what happens? The direction of deflection also reversed. From these experiments, it was not a planned experiment conducted by H.C. Ørsted, Hans Christian Ørsted. He accidentally noticed that when a compass is placed near a current carrying conductor, it undergoes deflection, and when the direction of current is reversed, the direction of the rate of deflection in the compass needle is also reversed. Okay, and thus he accidentally proved that a current carrying conductor produces certain magnetic property as same as that of a magnet. Okay, so it was Hans Christian Ørsted who accidentally proved. Accidental discoveries. There are a lot of accidental discoveries in science. Okay, and these accidental discoveries are commonly called as serendipity. Serendipity. Okay, and this was also a serendipity by Hans Christian Ørsted. That is, he accidentally identified that a current carrying conductor produces a magnetic field surrounding it. There is some magnetic field surrounding this current carrying conductor, which causes a deflection in the compass needle. So, who first identified the magnetic property provided by a current carrying conductor? It was Hans Christian Ørsted. Okay. You just notice that, not that Hans Christian Ørsted was the first person who identified the magnetic property. Hans Christian Ørsted identified the magnetic effect of a current carrying conductor. Okay, magnetic effect of a current carrying conductor was first identified by Hans Christian Ørsted. Okay, and later, after this identification, that is after this discovery, other two scientists, BIOT and SAVARTZ, another two scientists, BIOT and SAVARTZ, discovered or studied about this magnetic property shown by the current carrying conductor. And finally, they reached up to a law called as BIOT-SAVARTZ law, which is a very important basic law in our moving charges and magnetism. Okay, so we have to start our chapter from BIOT-SAVARTZ law. So at first, note this. Okay, so who identified the magnetic property shown by a current carrying conductor? It was Hans Christian Ørsted. And who studied this magnetic effect produced by a current carrying conductor in detail? BIOT and SAVARTZ. Okay, so we are going to BIOT-SAVARTZ law. Very important law. BIOT-SAVARTZ law. Okay. They had taken a current carrying conductor which carries a current I. Okay, so this is a current carrying conductor carrying a current I. There is a point P which is at a distance R from a very small segment of this current carrying conductor. So this much is the length of the conductor and the remaining part is also present. Whatever may be, from this conductor, they had taken a very small segment of length dl. This segment is of length dl. So this is a very small current carrying segment of length dl which carries the current I. The current is same throughout the conductor. So I current flows through this segment also. And this segment, current carrying segment, produces a magnetic field at point P, which is at a distance R from it, and it makes an angle theta. The position vector between the segment and the point makes an angle theta with the direction of current. Clear? This is the position vector between the point and the current carrying segment. BIOT and SAVARTZ discussed about the magnetic field produced by a very small segment. Not about the total current carrying conductor, but the magnetic field produced by a very small segment, current carrying segment. They had taken a very small, they had taken a very small current carrying segment. If you want to name, take it as AB. A very small segment AB of length, a very small segment AB of length DL, which carries a current I, with a point P, which is at a distance R from the segment, and its position vector makes an angle theta to the direction of the current. To the direction of current, this is the direction of current. May I take my reading? This is the direction of current at this point, and to this direction of current, take the tangent here. It makes an angle theta. Okay, so what we have taken according to BIOT and SAVARTZ, they had taken, that is, they had considered a very small current carrying segment of length dl, carrying a current I. Okay, P is a point. This is law, that's why I am writing full. P is a point. which is at a distance, r from the segment, making an angle theta with the direction of current. So what we have taken, BIOT and SAVARTZ have taken a current carrying conductor. From that, consider a very small current carrying segment of length dl. Carrying a current I. Then P is a point which is at a distance r from the segment, making an angle theta with the direction of current. Okay, if so, this current carrying segment produces a magnetic field at the point P. The magnetic field is represented by, what is magnetic field? What was electric field? It is the region. Yes, you have to say it is the region around a charge where another charge experiences a force of attraction or repulsion. Similarly, what is magnetic field? It is the region around this current carrying conductor where a magnetic substance like compass needle placed at P shows it experiences a magnetic force. Okay, so what is magnetic field? It is the region around a magnet or a current carrying conductor where a magnetic substance experiences the magnetic property. Okay, if you want the definition of magnetic field, you can write magnetic field is the region around a magnet. Normally, magnetic field is provided by a magnet. But here we are going to magnetic field of a current carrying conductor. Therefore, we can define magnetic field as the region around a magnet or a current carrying conductor. The region around a magnet or a current carrying conductor where a magnetic substance experiences the magnetic property or magnetic force. Okay, and the magnetic field is generally represented by the letter B. Which letter is used for magnetic field? B is taken for magnetic field. Which letter was used for electric field? E was taken. Similarly, which letter is used for represent magnetic field? B is taken. Okay, clear? So we know what is magnetic field and its representation. Magnetic field is the region around a magnet or a current carrying conductor where a magnetic substance experiences some magnetic force or magnetic property. Clear? Okay, represented by the letter B. Now, BIOT and SAVARTZ were talking about the current carrying conductor segment, that is a very small segment AB. It produces a magnetic field at the point P, which is at a distance r, making an angle theta to the direction of current. So the magnetic field produced by this small segment is also very small. The magnetic field is also very small. So we can write here the magnetic field dB. Why dB? Because the current carrying segment has a very small length dl. The magnetic field dB provided by this segment is, okay, dB is proportional to the current I. Initially they found that from experiments they found that dB is proportional to I. dB is also proportional to, here we can write, okay, dB is proportional to I, dB is proportional to the length of the segment dl, dB is proportional to the sine of the angle theta, whereas dB, can you see here, so I will write here, dB is proportional to 1 by r square, that is inversely proportional to the square of the distance between the segment and the point. Clear? So from experiments, BIOT and SAVARTZ proved that the magnetic field dB produced by the very small segment, current carrying segment of length dl carrying a current I at a point P, which is at a distance r from it, making an angle theta to the direction of current. That magnetic field is proportional to the current I. It is also proportional to the small length dl. It is also proportional to sine of the angle between the position vector and the direction of current. It is inversely proportional to the square of the distance. This was the law given by BIOT and SAVARTZ. So, how can you say BIOT-SAVARTZ law? According to BIOT-SAVARTZ law, the magnetic field dB produced by a very small current carrying segment of length dl carrying a current I at a point P, which is at a distance r from it, making an angle theta to the direction of the current, is dB is directly proportional to the current I. It is directly, where is my blue pen? Yes, here it is. dB is directly proportional to current I. Oh, sorry, this is not blue. Yes, this is the blue. dB is directly proportional to current I. dB is proportional to the length dl. dB is proportional to sine of angle theta. dB is proportional to 1 by r square. Clear? Okay. So, have you written this? Pause the video and take the notes. Okay, I'm going to rub that. So, the magnetic field due to a very small current carrying conductor AB of length dl carrying a current I at a point P, which is at a distance r from it, making an angle theta to the direction of current. Okay, that is dB is proportional to I. dB is proportional to the length of the current carrying segment dl. dB is proportional to sine of the angle theta. dB is inversely proportional to the square of the distance. And all together we can write dB is proportional to I dl sine theta, whereas inversely proportional to r square. So finally we can write dB is proportional to I dl sine theta by r square. And changing the proportionality, we will get a constant. And that constant is taken as mu 0. Mu 0, and is called as the permeability. In electric field, we have studied about epsilon 0, permittivity of free space. And here mu 0 is the permeability of free space. Okay, permeability of free space. Mu 0 by 4 pi, which is the constant in the BIOT-SAVARTZ law. Mu 0 by 4 pi I dl sine theta by r square. Okay, so dB is equal to mu 0 by 4 pi I dl sine theta by r square. Clear? Where mu 0 is the permeability of free space and its value is equal to 4 pi into 10 raised to minus 7. What is the value of mu 0? Mu 0 has a value of 4 pi into 10 raised to minus 7. Therefore, what is the value of mu 0 by 4 pi? Mu 0 by 4 pi becomes 10 raised to minus 7. So, mu 0 by 4 pi is equal to 10 raised to minus 7. Therefore, BIOT-SAVARTZ law may also be taken as dB is equal to 10 raised to minus 7 I dl sine theta by r square. The equation is important. I dl mu 0 by 4 pi. The basic equation of moving charges and magnetism is dB is equal to. Remember, dB is the magnetic field produced by a very small segment. Okay, dB is equal to mu 0 by 4 pi I dl sine theta by r square. Okay, so may I rub? So, from the BIOT-SAVARTZ law, we got the magnetic field due to a very small current carrying segment, dB. dB is equal to the equation for magnetic field due to a very small current carrying segment. dB is equal to mu 0 permeability of free space by 4 pi I dl sin theta by r square. Clear? dB is equal to mu 0 by 4 pi I dl sin theta by r square. The magnitude of field due to a very small current carrying segment is obtained by the equation mu 0 by 4 pi I dl sin theta by r square. Now, this magnetic field is a vector quantity. Before that, what is the unit of magnetic field? What is the unit of magnetic field? In SI unit, it is Tesla. Tesla, represented by capital T. Whereas in CGS unit, it is Gauss, represented by capital G. We want SI unit, but sometimes the numericals are given in Gauss also. The SI unit of magnetic field is Tesla and the CGS unit is Gauss. Okay, and 1 Tesla is equal to, we want the relation connecting Tesla and Gauss also. 1 Tesla is equal to 10 raised to 4 Gauss. Important. Okay, 1 Tesla is equal to how much Gauss? 10 raised to 4 Gauss. Clear? So now we know the magnitude of the magnetic field, the unit of the magnetic field, both in SI system and also in the CGS system. And now we are going to the direction of magnetic field. Mirror? Okay, direction. So already during the H.C. Easter's experiment, when the direction of current was reversed, the deflection in the compass needle was also reversed. We have studied that. We have observed that. That means our magnetic field is a vector quantity. Now we are going to the vector representation. Now we are going to the vector representation of magnetic field. In vector form, it is written as vector dB is equal to mu 0 by 4 pi I, listen, dl vector cross unit vector r cap by r vector square. Understood? How to write? Mu 0 by 4 pi is a constant, no vector form. Current is a scalar quantity, no vector form. Now, the vector form is represented as dl cross r. What is the magnitude of dl cross r? dl cross r cap, it is equal to dl into, this is into, not cross, whereas this is cross. dl into, what is unit vector r cap? It is 1. So, into 1. Cross product means sin theta. So, dl into 1 into sin theta. dl into 1 into sin theta. Again, it becomes dl sin theta. Correct? So, in vector form, it is represented as vector dB is equal to mu 0 by 4 pi I dl cross unit vector r cap by vector r the whole square. Now it shows the vector form of our magnetic field. Clear? So this is the vector representation. But from this vector representation, can you mention what is the direction of the magnetic field? This is only the representation. Now, in order to find the direction of magnetic field, there is a rule called as the right hand thumb rule. Right hand thumb rule. Thumb rule. Hoping you have studied this in your 10th standard. Right hand thumb rule. So, what does this right hand thumb rule states? Right hand thumb rule states that, suppose this is a straight current carrying conductor. This is a straight current carrying conductor. Then take your right hand and in this hand, thumb represents the straight line and fingers, the 4 fingers represents the curlings. The curlings like this. That is, according to right hand thumb rule, if a straight current carrying conductor, this is my straight current carrying conductor. If a straight current carrying conductor is placed in my right hand in such a way that thumb directs towards the direction of current, current is in the upward direction, thumb directs towards the direction of current, then the curlings of the finger, the curlings of the finger will give the direction of magnetic field. If this is the straight current carrying conductor, current in the upward direction. Take your right hand, this is the direction of the current. Okay, thumb in the direction of current. Then fingers curl it like this. So this is the direction of the magnetic field surrounding the conductor. Okay, so if the conductor is straight, field will be round. Or suppose I have taken a circular current carrying conductor. Now, curlings is given by the fingers. Now, rotate the fingers, the 4 fingers in the direction of current like this. Can you see? Okay, the 4 fingers are rotated in the same direction of the current. Then the thumb points outside. That is, the thumb is out of the plane. The magnetic field is towards you. If the current is straight, field will be round, circular. If the current is circular, field will be straight, vice versa. Current is straight, field round. Current round, field straight. Okay, clear? So, right hand thumb rule states that if a straight current carrying conductor, we are talking about straight, but if the circular current carrying conductor is given, take that. So, according to the right hand thumb rule, if a straight current carrying conductor is placed in our right hand in such a way that thumb points towards the direction of current, then the curlings of the finger will give the direction of the magnetic field. Once more, current in the direction of thumb, then the curlings of the finger will give the direction of the magnetic field. Okay, you may write. Vector representation is this, but the direction of the magnetic field is taken by using right hand thumb rule. Right hand thumb rule states that if a straight current carrying conductor is placed in our right hand in such a way that the thumb directs towards the direction of current, the current is in upward direction, then the curlings of the finger will give the direction of the magnetic field. Okay, if the current is towards this direction, then thumb towards the direction of current, curlings of the finger will be like this. Okay, if the current is in downward direction, thumb downward, the curlings of the finger will be in this direction. If the current is in this direction, thumb in this direction, the curlings of the finger will be like this. And if the current is circular, then rotate the fingers. This is the direction of current, thumb gives the direction of the magnetic field. If it is in anti-clockwise direction, if it is in clockwise direction, this was anti-clockwise. If it is in clockwise direction, tell me, fingers, rotate the fingers in the direction of current. The thumb will give the direction into the plane. Okay, so if one is straight, other will be circular. If the current is straight, field will be circular. If the current is circular, field will be straight, which is given by right hand thumb rule. This rule is also called as Maxwell's corkscrew rule. That is, if you rotate a screw, corkscrew, then it's a tip movement. The movement of the tip will give the magnetic field direction. Okay, the best way is to take a right hand thumb rule because your right hand is always in your hand. So there is no doubt. Okay, clear? So we were discussing about the BIOT-SAVARTZ law. Today we have talked about first one. For the first time, the magnetic effect of current carrying conductor was discussed by whom? By Hans Christian Easton. He accidentally placed a compass near a current carrying circuit. Then there was a deflection when the circuit was closed. When the direction of current in the circuit was reversed, the direction of deflection also reversed. From that, he proved that a current carrying conductor produces a certain magnetic field. Next, what is the definition for magnetic field? It is the region around a magnet or a current carrying conductor where a magnetic substance experiences certain force of attraction, repulsion or some magnetic property. Clear? Then, we have to study the Biosava's law. The first topic in our chapter is Biosava's law in detail. They had taken a very small current carrying segment of length dl, carrying a current I. A point P which is at a distance r from the current carrying segment, making an angle theta to the direction of current. Then the magnetic field dB is directly proportional to I dl sin theta by r square, or dB is equal to mu 0 by 4 pi I dl sin theta by r square. Clear? Then the unit of magnetic field in SI system, it is Tesla. We have to use Tesla always. But sometimes the numericals are given in CGS unit Gauss also. So what is the conversion? 1 Tesla is equal to 10 raised to 4 Gauss. Moreover, magnetic field is a vector quantity. So what is the vector representation? Vector dB is equal to mu 0 by 4 pi I. Then inside the bracket, vector dl cross r cap by vector r square. Clear? And this is just the representation. How to take the direction? By using the right hand thumb rule. And the right hand thumb rule states that if a straight current carrying conductor is placed in our right hand in such a way that the thumb directs towards the direction of current, then the curlings of the finger, C-U-R-L-I-N-G, curlings of the finger will give the direction of the magnetic field. If the current carrying conductor is circular, rotate the fingers in the direction of the current, then the thumb will give the direction of the magnetic field. Clear? So today we have discussed Biosava's law, the very important law, the most important law in moving charges and its magnetism. Okay, so till the next class, you have to study this very well. Very important topic, very interesting topic. Okay, and till the next class, study well, stay well, and this is our channel, Physics Gallery. Asha Binu. See you.